Hi there, this is exercise 6E.3. We've looked at quite a bit on circles and tangents and normals and the like already. We're going to use them here with some circle theorems we learned at GCSE. So it's not surprising, I suppose, that some of the circle theorems that we saw at GCSE come up again at A-level, but there's not much of it. But in this topic they do appear. And for instance, here's one that you may remember, that a tangent to a circle. Yeah, in fact, there's two tangents to a circle. When two tangents hit a circle like this, they always do so with a line of symmetry down the middle. So that's worth knowing. That will always be symmetrical. Another rule is that a tangent will always meet the radius. Notice this is going to the origin of the circle, the centre of the circle, and it will always do so at 90 degrees. So there's two rules already that we learnt at GCSE. First of all, it is a little starter view. It says what is special about the following circles. I want you to think about this. You might, some of these you're going to have to try to draw, because otherwise I don't think you'll know what's going on. So try and draw these circles. This one's easy enough because you know the centre of the circle. The centre on this, you can just take it from this, 3,7. And of course the radius of this is, it's always the square root of this number, so it's 3. Now think about what that means in terms of the picture. This one you're going to have to complete the square, and this one you're going to have to complete the square. So I've given two of them for you to do, and you're going to have to complete the square on both. And on this one, again, it's a bit easier, this one, because I've done a lot of the work for you. So B and C are certainly, you've got to do a bit of maths. That's 4, minus 3. And here the radius is 5. So I want you to think about why those are special. So pause the video and give yourself a chance to do it properly. Obviously make sure you do proper algebra and take proper notes. Don't just copy down. Okay. Hopefully you've done that now. If you haven't, make sure you do so and you pause the video. But if you have done that, I'm going to just give you a few clues. The first one, I've said the circle touches the x-axis, the y-axis, sorry. So here the centre is 3,7, which is up here somewhere. But the radius is 3. So the radius of 3, you can see it basically goes around like that. Not my best circle ever, but you get the idea. So because it's got the same radius as it is away from there, it will touch in that place. This next one, it says it touches the x-axis. Well, first of all, I suppose you should have written this down as x squared plus 2x and y squared minus 10y plus 1. And I can tell you straight away from that, I'm going to get the centre, the centre will be at minus 1. Notice it's half of this 2, that's basically y, and plus 5. And the radius, well, that's a bit harder to do, because if you're going to do this, you'd get x plus 1 all squared. I'm just going back to the basic now, take away the 1, plus y minus 5 all squared. So take away 25, plus 1 equals 0. And you notice that plus 1 and that minus 1 disappears. So really that 25 moves over, and therefore the radius is the square root of that, which is 5. Okay, what's that look like? I've got minus 1, 5, so it's up there somewhere, and it's got a radius of 5. Alright, I see. So it looks like that. It just touches there. Not my best circle. I'll do the same thing for this, because this is x plus 8, so it's 4 all squared, minus 16, plus, I've got 8y, so it's y plus 4 all squared, minus 16, plus the 16 equals 0. Well, first of all, I think they cancel out. That moves over. I think the centre here, well, it's plus 4, so I reckon it's minus 4, minus 4. And it's got a minus 16. I reckon the radius is 4. So I reckon it actually touches both axes this time. Minus 4, it's down there. And the radius is 4. I reckon it touches both axes like that. Yeah, both x and y axis. This last one, actually, you might have sussed it. If I draw it, 4, minus 3 is there. But this distance here, by Pythagoras, that we know is 4 across. This we know is 3 down. If you do Pythagoras, that is 5. And therefore, since the radius is 5, my circle goes exactly through the origin. That happens, you can't quite read it, but circle passes through the origin. That happens more often than you'd give it credit for. Anyway, perpendicular bisector chord. This is a rule that you learnt at GCSE. If you draw a chord is just a line that cuts through a circle, and if you draw a radius through the middle of it, that's why it's called a bisector, because it cuts it exactly in two. It will do so at right angles, and each side will be the same length. That's basically what it says. We are sometimes asked to find 3 points on a circle, and the one way we do it is using that perpendicular bisectors method that I just talked about. So if you want a circle which goes through 3 points that you are told, this is basically the idea. You find this perpendicular bisector for this line AC, and you find another one for AB. Now, because we know this line will cut it right through and go through the center, and this will also do it at the center, it's effectively give us a way to find the center of the circle. That's the plan anyway. So I here have got an example. It says the point 6,2. What's that? That's A. So this point here is 6,2. B is 8, minus 2. And C is 0,2. All right. The mere fact I've given you a nice one. Look, both of them are 0,2, 6,2. Can you see this goes straight across this line? Now, because I know that, I can actually tell you straight away what this point is here, because it's just the midpoint, obviously, and it's 0. I reckon it's 3,2. So we've got a point there which is at 3,2, and its chord, this line going across, this is called a chord, has got 0 gradient, and so this has got infinite gradient, if you like, and therefore this line here goes straight down. I suppose basically because that goes straight across, this goes straight down, and this line is called x equals 3. That's made it a lot easier for me. This line here, this chord, will cross again, splitting it exactly in two, a bit like this one was meant to do. And this point here, well, we can find its midpoint. We've seen this before. You add these together, 6 and 8 is 14, half of it is 7. Always half. You add them together and half. So 2 and minus 2 is 0. Half it is 0. So I've got that point there as well. Now finding this line is actually trickier. Now I've got to use the fact that I know it's the normal of my chord. My chord, I can find the gradient of that. The gradient of AB. Well, you just do what's the difference in the y and divide by the difference in the x. So 2 divided by, I reckon it goes down 4 basically. It goes down 4, so they'll call it minus 4. And it goes from 6 to 8, goes 2. I reckon the gradient of that is minus 2. So now I know that gradient is minus 2. The gradient of this line, because it hits at 90 degrees, the gradient of this line has got to be the negative reciprocal. That's of minus 2, that's a half. So I now know that gradient. Now, I can actually find that equation as well. I'm going to do it up here because I probably haven't got any room. The gradient is a half, and therefore the equation of the line uses this formula. You should remember this formula. Now, do we have a coordinate on this line? Well, luckily we do. We know it's 7, 0. So I can write y minus the y number is 0. The gradient is a half. X minus, what was the x number? It was 7. Move the 2 over. That's what we've been doing. 2y. Technically it's 2 zeros as well, but obviously that disappears. 1 times the x is x. 1 times the 7 is what? Minus 7. So that's my equation of my line. Or actually you can see x equals, if I move that over, 2y plus 7. Now you don't normally write it as x equals. But the reason why I want to is because I know this line hits this line at my center. And my center can be found if I solve these equations simultaneously. And of course I know this line's x is 3. So I've got x is 3, I've got x is this. You can see I can go 2y plus 7 equals 3. If x equals this and x equals that, then this equals that. Solve this equation. 2y equals 4. Oh, minus 4, I need to get it wrong then. Y is minus 2. So my coordinate of this point is 3, minus 2. Let's see if I agree with that. I've got some answers on this somewhere. And that was the Oh right, the one thing I haven't yet done, it says it wants not just the center, it wanted the actual equation of the circle. Alright, and so just go back a step. You've seen the answer, but it should make common sense. We now know the center is 3 and minus 2. So x plus, no, it is plus 3 here. So we write minus 3 all squared plus y. It says minus 2, so we'll have a plus 2 all squared. Now I need the radius. Do I know how big the radius is? I can pick any point. One thing I'm noticing is that there is 3, minus 2. And this over here, actually I haven't drawn it very well, this is 8, minus 2. You can see that is a radius. And technically they're both meant to be at the same height. So the distance between them is just 5. So therefore equals 25. Because you square it. Yes, that's what they had. So more circle theorems for us to have a look at. Angle in a semicircle rule. Now this is a rule that came up loads at GCSE. And basically, you can see I've split this circle into 2 semicircles, and I've done that by just drawing a simple diameter through the middle, or one semicircle or another semicircle. So if I just look at part of it, one of the sides, one of the semicircles, and I draw a point anywhere I like. Now I've drawn it there, it could have been there, anywhere. If you draw the triangle to that point, you always get a right angle up in this corner. So that's a useful formula to know. There's another one, see? Still a right angle. If you get 2 tangents, this is what I explained at the start, 2 tangents, you always get this line of symmetry, and you always get these right angled. So this is quite a common picture. You know that one side of this line is the same as the other, so if I know this angle, I know this angle, if I know this angle, I know this angle. I know these are both 90, because a radius will always hit a tangent at 90 degrees. That's definitely worth knowing. And you are very often, because it's... look, I've got a right angle triangle, so I've got potential. If I know some of these points, I've got potential to actually find something out here using Pythagoras' theorem, because I know this squared plus this squared is this squared, and that often comes up as well. So this question, I'm not sure if we'll get a chance to finish it, but we can start it. A, B, C are the points 3, 5, yep, 2 minus 2, 4, and 1, 2. Use gradients to show that the C lines on a circle with diameter AB. So they're suggesting there's a circle that goes through them like that. Now it says it's got a diameter AB. Now how could I do that? Well, they lie in the circle, I suppose. If I find the gradients, so I'll do MAB first of all, and you will recall I basically take 5, I work out how far up they go 1 up. How far across? It goes from minus 2 to 3. It goes to 5 across. So I know that gradient is a 5th. Now, do I want that? Actually, I just realised I didn't want that. What I wanted was this gradient. That's worth knowing. And this gradient. Because I've just realised they want me to use gradients. And the trick they use is that because this has got to be a right angle if it is a semicircle, and therefore is a diameter, then this gradient and this gradient must have a rule which is their gradients are negative reciprocals of that. So I'll do MBC. Again, it goes down this one. It goes down, if you look, from 4 to 2, so it goes down 2. And it goes across from minus 2 to 1, that's 3. If I do MAC, now this goes down 5 to 2, that goes down to 3. It goes up rather, up 3, and 1 to 3, that's 2. And the posh way of showing this is I can say MBC times by MAC, the gradient of one of them times the gradient of the other one. And if you do this on your calculator, or just check that everything cancels, you get minus 1. And therefore it's a right angle. And once you know it's a right angle, you can therefore say it's an angle in a semicircle. And therefore it must be a diameter. Let's see what I've just write at the end. That's what I've basically written. So I don't think we're going to get through all of this. There's more to do, one more question in lesson as a starting point. But we'll have a look at exercise 6E and have a look at these questions and just try to finish off whatever's still missing. So I hope that makes sense. Good luck.